Differences in initial angular momentum can cause equatorial material to reach orbital speed before falling into the black hole, and thus forming a disk of highly energetic plasma.
Wow, that sounds complicated. So let's break it down. You might have to equip your mental running shoes for this one. To start off, let us imagine a newly formed black hole directly from the furnace of a supernova explosion. The gravitational force of the core will attract most of the surrounding material, as there is no other force keeping it from becoming absorbed by the black hole. Now instead, try and imagine what would happen if the black hole was rotating rapidly around its own axis, as it would if its ancestral star was rotating. To understand what would happen, we must first introduce the concept of angular momentum. Angular momentum is defined as a product of a body's rotational inertia and rotational velocity. What's important to know about it is that, unless there is some external force interfering, angular momentum is conserved. Now let us return to our hypothetical rotating black hole. The surrounding matter from the equator of the ancestral star would have a very high rotational speed indeed. This is in contrast to the matter around the axis of the ancestral star, which will be almost without any rotational speed. This means that when the equatorial material begins to fall towards the black hole, due to the conservation of angular momentum, when the distance to the black hole decreases, the rotational speed increases proportionally and eventually it will reach orbital speed. In contrast, most of the polar material will fall straight into the black hole. The result will be a disk consisting of incredibly fast material spinning around the equator of the black hole.